So, somehow these got out of order. Okay. Evaluating limits analytically. This is something that you began in pre-calculus last year at the very end of the year. Okay. So here are some basic limits. If you have the limit of a constant, it's going to be that constant, right? Do you remember when we did direct substitution? We just plugged in to see where that point was. Okay, we know graphically that if we have a coordinate, okay, that's obviously not an end point. If we have a coordinate on a curve, that's where our limit is going to be, right? So if we know where the coordinate is, then we know our limit. So if we have the limit of a constant function, if a constant function is just a horizontal line, our limits are going to be the same wherever it is. Okay, so here the limit as x approaches 2 of 5 is 5. Okay. Here the limit as x approaches c of x, okay, is c. Basically, what are we doing? We're plugging that value into our function to see where the coordinate is. So the limit as x approaches 2 of x is 2. Plug 2 in for x. Okay, same thing here, even on a polynomial function. Polynomials are continuous, so we're going to have points everywhere. We can evaluate the limit by just plugging in our value. The limit as x approaches 2 of x cubed is 2 cubed, which is 8. Okay? All right. Here are some properties of limits. Okay. These are things that we can do with our limits. Okay. If I have two separate limits that I've evaluated. Okay. If I have a multiple on my function, it's the same thing as evaluating the limit of f and multiplying by that scalar after. Okay. So you can do it before, you can do it after. Okay. What? Okay. Having a multiple, a scalar multiple in front of our function, you can evaluate the limit of f and then multiply it by the scalar. It means the same thing. Okay, whether it's inside or outside. Okay, I can add or subtract two limits together. We can multiply them together. We can divide them as long as our denominator is not 0. And we can take them to a power. Okay. These are in your book, so you can write them down. You can reference them. I don't care what you do. Just understand that these work in this way.
So for the product one, it would be the same as taking, if you found the limits separately, and then multiply them as if you would factor them together and find the limit of that. Okay.
Okay. So we're going to go back to this direct substitution business that I was talking about. Okay. We're going to talk about when we can use substitution, and then we're going to talk about times where we have to adjust for direct substitution. Okay. So if you don't have all of this down, I can either come back later or you can look in your book. But I want to make sure we have enough time to talk about all of our strategies here, okay? So we can use direct substitution to any polynomial function and any rational function as long as it's not going to make the denominator 0. Okay? So any polynomial function and any rational function where our denominator will not be 0, we can just do direct substitution. What does that mean? We take the limit as x approaches c of a function and we just plug c in. We evaluate the function there. Because that's where the coordinate is, that's where our limit's going to be. That's where we're approaching, that coordinate. Okay? So whether it's polynomial or rational, okay, as long as our substitution does not make this denominator 0, we can just plug and go. Okay? So we're going to do a couple examples. And these are examples like what you had last year in pre-calculus. They're supposed to be angled this way. So, okay. Does anybody need more time for
It's hard. It's hard. Yeah, I've just been like, I don't know.
Well, what I mean is like you can
There's a desk right there.
But I don't want to
keep
go
them like
being
this.
some of their ones. So.
Keep them like this, but just angle it from everybody.
I'll do it.
Okay.
No, there's so much.
Okay, so the limit as x approaches 3 of 3x plus x squared. This is a polynomial function. We can just use direct substitution. All we have to do is plug 3 in for x. And our limit is what?
18.
Done. Okay. Here, I have a rational function. Does 3 make my denominator 0?
No.
Then we can use direct substitution.
27.
27.
Okay. Now, what happens? We're going to need a separate strategy for if it does make our denominator 0. So we will talk about that here in about 3 minutes. Okay? Another time where we can use direct substitution is if we have a radical function. Okay? As long as, okay, so we've talked about polynomials, we've talked about rational functions. If we have a root function, okay, a radical, we can still use direct substitution as long as we still have a real number, okay? Obviously, I cannot evaluate the limit as x approaches -2 of the square root of x because we have nothing there, all right? So as long as it's going to give you a real number, then that is okay, okay? So here we have the limit as x approaches 3 of radical 3x squared, okay? All we have to do is direct substitution, 3 times 3 squared. And what would you give me for an answer?
Answer is 3 squared.
Just 3 radical 3. There's no plus or minus. We're not solving. We're just we're just simplifying. Okay? So direct substitution when we have radical equations, when we have polynomials, and rationals where our denominator is not 0. Okay. So, what happens if our denominator is 0?
It's either a whole,
It's either a whole or an asymptote. If it's an asymptote, then we're kind of out of luck, right? Because at an asymptote, we have unbounded behavior. Do you agree?
Yeah.
Okay, unbounded behavior means our limit fails to exist. So only if we have a whole can we evaluate the limit. Even if we have a whole, as long as we're approaching the whole from the right and left, to get there, that limit is going to exist. Okay? So, this is similar to what we saw yesterday, right? We looked at the graph yesterday, and how did we graph it? what did we have to do?
Or-
We factored first to see if any factors cancel. That's going to be our same strategy when we're evaluating limits analytically, okay? So I can factor upstairs x plus 2 times x minus 2. And do we have factors in common?
Yes.
Okay, that means, okay, first of all, I guess I should back up. We can't use direct substitution because 2 makes our denominator 0, right? We factored, we canceled out factors, so what's happening at x is 2? We have a whole. So what we can do is we can now evaluate the limit as x approaches 2 of x plus 2. Can we use direct substitution here? What is it?
4.
It's 4. Okay. You don't have to graph it, but let's talk about why it is 4. Okay? Since these factors canceled, we're talking about the line y equals x plus 2. But we have a whole there at 2, 4. So the limit as x approaches 2 is 4 because that's where your whole is. It's a horrible line, but you get the idea. Okay? So, if it's a rational function, check to see if your direct substitution makes your denominator 0. If it does, see if you can factor so you can cancel out factors and then use direct substitution. But if it doesn't make your denominator 0, don't go through that work. Just plug it in. Okay? Maybe you remember seeing something like this last year.
Maybe. Oh.
Okay? Maybe, maybe not. So first of all, we have a rational function. Does our c value make our denominator 0?
Yes.
We cannot use direct substitution yet. However,
Conjugate.
we can multiply by the conjugate, which is what?
X plus 1
Square root of x plus 1
Plus 1.
plus 1. Okay. What's the point? Well, let's see what happens. Remember, if we get factors to cancel, that means we have a whole at 0. So that's what we're hoping to have happen. So what's the square root of x plus 1 minus 1 times the square root of x plus 1 plus 1?
That would be x plus 1.
X plus 1
Minus
minus 1. A squared minus b squared. Right? Okay. What is x plus 1 minus 1?
X.
Oh, and I have an x right here. Do you agree?
You
So
did.
not only do those 1 minus 1, that cancels out to 0, we have an x over x. So now this becomes the limit as x approaches 0 of 1 over square root of x plus 1 plus 1. Those x factors canceled, which means we have a whole there. Okay? Can I now plug in 0 and get a legitimate value?
Yeah.
Yes. When I plug in 0, what do we get?
4
So our limit is 1/2. So Dana, did you have a question or did you get it? Okay? Everything we've done so far, you saw last year, correct? Okay. Let's do something new. Limits of a composition. Okay. Composition function, f composed with g, right? We are going to evaluate limits of a composition much like we evaluate compositions. We always start from the inside and we work out, correct? So first of all, if we have the limit as x approaches c of g of x, we're going to say that it equals L. Notice how I'm starting with g of x. And let's say that the limit as x approaches L of f of x, you want it to be k? Okay. It can be k. Okay? Okay, so then what does this mean? The limit as x approaches c of our composition. Okay? We first evaluate the limit of our inside function. So we evaluate the limit, well, we have f of the limit as x approaches c of g of x.
Is it the limit of that value?
Huh?
Is it the limit of that value? Or is it just
Technically the limit, because what we're going to do is we're going to evaluate the limit of g, and what are we going to get that to be? L, right? And so you can say it's the limit as x approaches L of f, right? Which, if we're using direct substitution, would just be f evaluated at L, okay? If we're not using substitution, then we still need to take, okay, the limit. So we take the limit of our inside function. That's going to give us where we're taking the limit of our outside function. That's going to give us this new value right here. Okay?
But if we're taking, if the limit is usually a y value, right? Then why is it going into the x value of the function? That's just how it works,
Well, because this gives us L, right?
right?
Which is like this f of L.
But why are we putting a y value into x?
Because that's what a composition is. We take what we get, we take the y value of our inside function and we plug that in for our new function. You with me?
Yep.
Okay. So here are our two functions. The square root doesn't work very well in this program, so I made it work, but not very well. Sorry. Doesn't matter what it looks like, just that is what we get. Okay, so I would like, okay, first of all, what is the limit as x approaches 2 of f of x over g of x? How do we do this? Yes.
you plug in the function?
Okay. We can do each of these limits separately, correct? What's the limit as x approaches 2 of f of x?
8.
Over, what's the limit as x approaches 2 of g of x?
Oh, that's cool. Flip the.
Which is forced for
Yeah,
the
flip on.
Okay.
8 radical 2 of 2. 4 radical 2. Oh, yeah.
Okay. Okay. That was just our warm-up. Okay. So, first of all, what do I need to evaluate?
G of x. Limit of G of x.
Okay. So, side note, what is the limit as x approaches 2 of g of x?
Square root of 2.
Okay. So for this composition function, since this limit is square root of 2, we're now going to take the limit as x approaches radical 2 of our outside function, f of x. Okay? So we take the limit of the inside function to give us our new c value for the outside function. So now when we use direct substitution, what's the limit as x approaches radical 2 of f of x?
6.
Okay, I would like you to find me the limit as x approaches 3 of g composed with f. Do you need the functions, or do you have them? The limit as x approaches 3 of g composed with f. I had trouble writing it, sorry.
Is that G of X?
Yes. I need to at least see one step. I can't just have an answer. I need at least one step here. Like, this is like the one step I would need to see right here. Okay, so Aaron Lawrence, what is that one step I would need to see? Say it out for me.
The limit of x approaching, and I did these wrong, so I used 2 instead of 3 still. So, whatever that is, of g of x.
Help him out. What number should be here?
3. 3. Oh.
Because we have to evaluate the limit as x
Yeah.
approaches 3 of f of x.
Yeah, I was being dumb.
So this limit is.
Square root of 15.
Alright, go ahead. All right. Now everyone's favorite part.
Yeah.
The difference quotient.
Yeah.
Okay. Now, you may see it like this. You may see it instead of delta x, h. They mean the same thing. Delta x, what does delta x mean? Change in x. Okay? Which is the same thing as what's the height difference. That's what h stands for. Okay? You need to know, first of all, what the difference quotient looks like. Second of all, how to take the limit of it. So you need to know f of x plus h minus f of x all over h, or delta x, whatever. But you need to know that that is the difference quotient. It is very important in this chapter and the next chapter. Okay? Okay, this is the foundation for the beginning of Unit 2. All right? We are going to take the limit of the difference quotient for our function 2x plus 1. I'm going to make it easy on you. We have a nice linear function. Our algebra isn't going to be too difficult. Okay? When I gave you this difference quotient in your homework, on your test, what always happened?
The x's and the ones cancel.
Okay, either the h, or in this case, the delta x will cancel. Okay? Why? Because you need to evaluate the limit as it goes to 0. So no matter what, your algebra should get these to cancel out. So here we go. We are going to do this with delta x's though. The limit as the change in x approaches 0. F of x plus change in x. So we have 2 times x plus change in x plus 1. 2x plus 1. Minus, please be careful, you're subtracting the entire function. Please put it in parentheses. All over our change in x. Okay. So we have the limit as delta x approaches 0. We have 2x plus 2 delta x plus 1 minus 2x minus 1 all over delta x.
So do you do that every time that it says the change of x on the number?
What's your question?
Like, do you do the difference quotient every time that it's the change of x, or is that just?
Numbers the difference.
This is the limit of the difference quotient. Is that your question?
Kind of. I didn't answer it.
Okay. So you're okay. All right. What happens? So we have 2 delta x over delta x, which is
2. Yes.
so what's the limit as delta x approaches 0 of 2?
2.
Okay. Where you need to be careful is where we have like maybe a square or a cube thrown in there. Okay, because you're going to have that binomial being squared or cubed or whatever it is, okay?
There it is.
Please be very careful with your algebra. Okay, one of the hardest part about calculus is the algebra, so please keep everything organized. Okay? Here is your homework. Okay? You're going to have evaluating limits analytically. Okay? I've shown you a couple tricks. All right, and then you're going to have the limit of the composition, the limit of the difference quotient. Okay? You can always use direct substitution. We talked about 3 times. What are those times?
Polynomial.
Polynomial,
When it doesn't make the denominator 0.
irrational where the denominator is not 0.
And something where it doesn't cause an imaginary answer.
Okay, well, we can have our root functions, right? Square root, cube root, fourth root, as long as we're not getting an imaginary there. Okay? If you have a rational, I've shown you some tricks to get factors to cancel out. Okay? You have the rest of the time to work.